Hello, good morning, good afternoon, and good evening. Welcome to another seminar in our Instant Insight series. My name is Troy Nickel, and I have the privilege to host our seminar today and introduce our speakers. Our topic is novel 3D printed liquid crystal elastomers, and it's a highlight of some of the research in the Smart Materials and Biomechanics Lab at the University of Colorado, Denver. Professor Chris Yakaki, Dr. Divesh Mistry, and Nicholas Dragut will be co-presenting on their developments in these elastomers. They will also be talking about the progress they've made to methodically measure their unique mechanical properties. After the presentation, I'll jump back in and facilitate a Q&A session. So please feel free to submit your questions using the Q&A tool in the lower left of your screen. I'll gather them up during the talk and then work through as many as we can after the presentation. Also, you can find some related product documentation by clicking the folder icon in the lower right of your screen. So, with that, I'll pass it over to Professor Yakaki to begin.
Thank you, Troy. And thank you all for joining us. This is the second webinar I've done with TA Instruments. I enjoy doing these. Hopefully you learned a little bit about some cool scientific research that we're doing, but also a little bit of how we characterize materials. I like to think we're materials folks. We'll try to highlight some pretty unique cases. I see some familiar names in the panel or the attendees list, so if we know you, we see you there. Thanks for joining in on us. I'll try to unpack this title a little bit. I know in science, oftentimes we try to give really long titles to make us sound smart. I'd say the focus is going to be on the liquid crystal elastomers. That's just a pretty interesting, I'd say, dynamic and unique soft polymer. And we'll explain some of their behaviors and why they're unique. 3D printing and additive manufacturing is something that we've really kind of invested in and dove deep into. And so we try to kind of combine both unique materials and unique manufacturing. And when we do that, characterizing that final product, I don't want to say it can be challenging, but you need unique equipment to do so. And so we'll run through different properties that we want to characterize and do. I'll briefly introduce us, the speakers. I'm Christopher Yakaki. I'm a professor at CU Denver. I have to do full disclosure. I do have a company, Impressio, that we're trying to actually commercialize liquid crystal elastomers into some pretty interesting devices. Some being helmets and protective helmets for football, as well as other things. Some being biomedical devices, and we'll give you a little sneak peek on maybe how these materials could do that in this presentation. We also have Divesh Mistry. He's a postdoctoral fellow under my lab. Divesh has just been awesome, and he really made some great strides towards our 3D printing with direct ink writing. And Nick Dragut. Nick is going to graduate here at the end of the year, hopefully, fingers crossed. So if anyone thinks, wow, he was a real smart guy and he knows a lot about synthesis of polymers and characterization and 3D printing, I know he's looking for either a postdoc or a job. So this is my shameless promotion for my students. So to kind of unpack the talk a little bit again, we'll give you a brief overview of what these liquid crystal elastomers are, kind of a little bit about their history, but then also why their behaviors are unique and interesting and maybe hard to characterize and a little bit different than what you might expect from soft polymers. We'll do just a brief overview of how we 3D print these materials. There's a couple different ways, and you can kind of see some sneak peeks, little pictures of us doing direct ink writing or a lattice that was done using DLP printing. And then for each of us, Divesh, Nick, and myself, we'll go over some use cases from different either studies we've already published or are actually in the process of publishing. And so, we'll try to cover everything from measuring dissipation of the materials to the rate dependence to doing cyclic behavior and maybe a little bit more in there as well. So without further ado, what I'm going to do is I'm going to hand it over to the physicist, Divesh. The physicists have really, they like to describe liquid crystals. I think, they were the pioneers in these fields. So we'll turn it over to him to explain what liquid crystal elastomers are. Divesh, take it away.
Okay, thank you, Chris. So as a place to start, let's start with just some crystalline and solid materials. I'm sure everyone here is aware of the fact that we have two different types of solids. So we have our crystalline solids where we have positional and orientational order, and amorphous solids where we lack that order, and they're our glasses. Liquid crystals are, on a simple level, nothing more than the ordered form of a liquid type material. So your amorphous liquids are things like water, things like oil, A liquid crystal is typically made from something like this molecule that's shown here, so often a rod-like molecule, and they pack together in a certain way which gives a sense of order inside the material, but also there is fluidity too. In about the 140 years since liquid crystals were first discovered, there's been quite an explosion, which we're all very aware of when it comes to LCD displays. Broadly speaking, there's two categories of liquid crystal systems. And so you have thermotropics, where we have transitions between these phases, which are some of them illustrated here. The transitions are mediated by changes in temperature. And down at the bottom, we have lyotropics, where these are formed from amphiphilic molecules, and the phase transitions are mediated by the concentration of these molecules in a solvent. Just a very brief note on the LCD industry, what makes it so successful. The responsiveness of liquid crystals, so in this case, the fact that the molecules will reorient in response to an electric field is the basis of what drives the changing optical properties, allowing pixels to be turned on and off. And so another example of a very similar rod-like molecule is shown there with the approximate size. Switching across to liquid crystal elastomers, what we are doing here is that we are essentially bonding these rod-like or typically rod-like molecules into a lightly cross-linked polymer network. And so there's one of two ways typically this is done. We have sidechain, where we have these mesogenic groups, liquid crystal groups, hanging as pendant from the backbone, and main chain when they're directly incorporated into that backbone. And the key thing that this does is that it changes the shape of the polymer random walk. So for a conventional polymer, you'll have an isotropic Gaussian polymer conformation. If you introduce the ordering from a liquid crystal phase, then what you get is an anisotropic polymer conformation. And that is really the basis of the mechanical properties and the actuation properties that you see in liquid crystal elastomers. Two specific cases to highlight are polydomain and monodomain. So like many crystalline types of material, if you don't do anything to instill a particular preferential direction of order, then you have these small domains which are misoriented with one another, and that causes a scattering of light, and so this top sample that's shown there has this milky white appearance. On the right-hand side is if we were to instill a macroscopic direction of order on the sample. So in this picture, it's achieved by stretching the sample. What we achieve is a monodomain system, and we have alignment across our entire material. And the two different options here, polydomain and monodomain, have different properties. If you've come across liquid crystal elastomers in the past, what you're probably most familiar with is their actuation behavior. And so what is happening is that as the liquid crystal order, so the order parameter, or the magnitude of ordering, is mediated typically by changes in temperature, that also has an impact on the shape of the polymer conformation. And that means that what you get are macroscopic shape changes, which is the basis of the soft robotic applications, for instance, that you commonly see. We won't be talking much about that in this presentation, or in fact at all, but there are a list of some references down at the side there in case you're interested. I will show two examples. We're just going to start a video here. Okay, and so what we have here is a UV activated liquid crystal elastomer, and as that film has been exposed to UV light, it contracts and it undergoes a isothermal change in its conformation, which causes it to grab that little object there. On the other side of things, we have a lifter here. So we have a especially patterned liquid crystal elastomer, and as that increases in temperature, it's lifting over 400 times its mass. So they're two kind of key examples for actuation. But what we're interested mostly in our department, in our group, are the mechanical behaviors of liquid crystal elastomers. So probably the most famous behavior is kind of summarized as being the inherent anisotropic and highly nonlinear mechanical behavior of liquid crystal elastomers. Specifically, so this idea of soft elasticity, where through a rotation of that polymer conformation, you can achieve a very soft response if you stretch perpendicular to the director. A phenomenon which I kind of found out about or discovered in my PhD was the negative Poisson's ratio behavior or ecstatic response of LCEs. And that's essentially where initially when stretching the material, we see, so if we stretch it perpendicular to the director, we see a positive Poisson ratio behavior, and then a transition where as we increase the stretch, it begins to grow thicker, so indicative of a negative Poisson's ratio. Interesting for several reasons because of the associated properties you might expect with that behavior. At CU Denver, what we're mostly interested in is the dynamic mechanical properties of LCEs. So this top graph here in the top right is showing a storage modulus versus temperature graph with also tan delta shown too. And the key thing to really highlight is that in this pneumatic range, although we see the drop in storage modulus you would expect as you enter an elastomeric regime, you also have an elevated tan delta plateau. And so that means we have a highly viscoelastic, highly damping material. I mean, that's why we're interested in these materials for biomedical, for sports, for any kind of vibration and mechanically damping application. Down at the bottom, we have another very interesting property, and that is the dynamic crystallinity of liquid crystal elastomers. So the fact that if you get the chemistry right, certain LCEs can display polymer crystallinity, and we can use that and use the controlling of the melting of those crystals and how those recrystallize. You can see these different curves here are showing recrystallization peaks via DMA, and we can use that in devices, and that's something that Chris will be talking about at the end of our presentation. So with that, I'll hand over to Nick to get us started on 3D printing.
Thank you, Divesh. So in Denver, or at CU Denver, we have a couple techniques we use when we're 3D printing our LCEs. We use digital light processing, and direct ink writing. When we're using DLP, we are making an isotropic genesis polydomain LCE structure, where the masogens do not print with any type of imposed order. And the reason that they're a polydomain is because we're diluting our photocurable resin in a solvent to bring down the viscosity to a more desired degree so that it works well with DLP printing. And the reason we like to use DLP printing is that we're able to make complex structures such as lattices, and we also maintain a high resolution while doing so. For DIW, it's a little bit more like fused deposition modeling, or FDM, except that instead of depositing a thermoplastic filament, it's depositing a photocurable resin, or as people call it, an ink. And what this technique allows us to do when we're printing LCEs is it allows us to impose an order on the masogens. And so the order occurs because as the resin is being extruded and deposited, the shear stresses that are applied to the masogens impose that order. And then the UV light will cure the resin and lock that order into place. And so we can have some directional order globally and locally. We recently published a study where we used DLP printing to look at dissipative lattice structures. We used DLP printing here for this study because we were able to show that we have control across several different length scales due to the high resolution. This figure shown is the first figure from our paper, and at the top we highlight the 3 different length scales that we were controlling during the study. And so from right to left we show that we can control the overall size and shape of the structure on the macroscopic scale, and then at the microscopic scale we can control lattice geometries. And then finally at the meso scale we're controlling the LCE chemistry, which will influence the mechanical properties as well. And so the first thing that we did was we printed some lattices, the first one being out of our LCE material, and then the other one being out of a commercially available resin, in this case Tango Black. We know that LCEs are elastomeric, and we have a good idea that they're also rate dependent. We also believe that they're going to dissipate energy better than traditional elastomers, so what we wanted to do was do a side-by-side comparison. And so in our lab, what we'll traditionally do after we make a new material is we'll start characterizing it by using the DMA. And so for our two materials, what we did was we did a temperature sweep on the Q800, and we just wanted to find out where these materials are equally elastomeric with a similar storage modulus so that we can perform our testing with a fair comparison. And so in that case, it was about a 28 degrees Celsius step above their respective glass transitions. And so what that meant was for the LCE, we were testing it at about room temperature, or 22 degrees, and then for Tango Black, it was approximately 42 degrees. So we used the Electroforce 3200 to characterize our lattice structures with some compression testing. We did 4 decades of varied strain rate, slow to fast. So for our first characterization, when we were looking at rate dependence, we took the stress values at 50% strain for each strain rate, and we used this rate dependency equation to help quantify rate dependence, where the quasi-static stress was the slowest stress, or sorry, the slowest strain rate of 0.21% per second. And so the figure on the left just shows you an example of our slowest and fastest loadings on one of the axes for each lattice structure. And you can kind of see the difference in the stress responses between the slow and the fast. And the figure on the right does a pretty good job of quantifying and showing visually what the big difference was between the rate dependence on each individual axes for each strain rate with the LCEs. So the LCEs were definitely much more rate dependent. And so with our testing, we wanted to test really fast because we're interested in things like impact velocities and stuff, and you can't achieve something like 220% per second on an MTS or an Instron or a Q800. And so that is why we chose the Electroforce to do our testing. And so we have on this next slide a video. And so when this video plays, in this video we're showing in real time what a square wave loading at a really high strain rate does. And we're just showing it with an elastomeric lattice structure that was being tested. And again, for example, like the MTS being screw driven, you're not going to be able to achieve that high of a strain rate. So if you're looking to do something really fast, the Electroforce is definitely the way to go. So what we also did with our compression data was we characterized our strain energy density. And so basically this was just a method of quantifying the mechanical energy dissipation of the materials. And then the strain energy density is the area under the curve for both the loading and unloading of the sample. And the plot on the left provides a graphical representation of what that area looks like. The plot on the right shows the strain energy density at our fastest loading rates for each axis of the LCE lattices and compares them to each axis of the Tango Black lattice. You can see that the LCEs dissipate significantly more mechanical energy than Tango Black, and that lattice geometry plays a significant role. So as mentioned previously, lattice geometry is something that we can control and can be a significant factor for mechanical dissipation. And so we have a quick summary of our study for DLP printing, and that is we showed that the LCEs are highly rate dependent and significantly more so than other elastomers like Tango Black, which while also being well above the glass transition temperatures and fully elastomeric. We also showed that LCEs dissipated more mechanical energy than Tango Black at the fastest strain rates we tested with. Again, We were only able to achieve that because of the strain rates that the electroforce is capable of putting out. And then with that, I will pass it back off to Divesh, who will talk more about our DIW printing.
Okay, so thank you very much, Nick. Just to kind of start, I'm just going to show you a video of some drop testing on one of our 3D printed LCE cubes, just to set the scene for what's going to come. So what we're showing here is a drop test of a 5 kilo mass from 1.8 meters or 6 feet. And what you're seeing is that it's basically from 1.8 meters of drop height, it's rebounding by about 36 millimeters. So we've absorbed a lot of energy, and what we're wanting to understand more going forward is why this is the case and what we can do with that. So if we'll just come back to the slides. So the things we know are that LCEs are very soft, and that we can program in anisotropy, especially using our 3D printer, our direct ink writing 3D printer. So that's in contrast to what Nick was talking about with the DLP printing, where we can achieve really high resolution and really intricate lattice structures, but we have no anisotropy unless you design it with the lattice structure. Here we're using the inherent molecular anisotropy, and seeing how we can relate that to the fact that biological tissues have very similar properties in terms of their symmetries, but also in their actual physical properties too. So we're interested in knowing what can we do with LCEs and how can we create devices. For instance, this little prototype device in the bottom corner of a 3D printed IVD intervertebral disc device. So there's two different kind of testing regimes which we're interested in this study. So with printed cubes, you can see on this picture here that the print direction is at 45 degrees to the loading direction. So printed cubes with various different orientations, and looking first of all at the tensile behavior, sorry, the compressive strain behavior over large strain. So with our electroforce, we were using, first of all, a program that would just increase the stress to 2 kilopascals, and that's just to identify where the top of the sample is, so it would find where to start from. And then from there, we would load out various different strain rates to be able to measure, looking at the initial modulus, first of all, but also, like what Nick was doing, how the strain energy density was changing with loading rate. On the other side of things, we're looking at the dynamic properties in respect to small strains, so DMA basically. So in a similar way, we're looking at just touching the top of the sample, and then also how does the dissipative behavior vary if we increase a pre-strain down to a certain level, as if it's loaded in a real environment. And looking at the different frequency ranges and how that affects our behavior. As a quick refresher, if you're not so familiar, if we're applying a sinusoidal stress or a dynamic stress, then the strain that we receive or the strain that we record there'll be a phase lag between the stress and the strain, and that's because of the viscoelasticity of the material. So if we don't have a phase lag, then we have a perfectly elastic system. If it's completely out of phase, and we have a perfectly viscous system. And a viscoelastic system will lie somewhere, obviously, in between that range. So I'm not going to show you all of the possible data we could do. We'll just highlight a few results here and there, which kind of shows what we're achieving with the equipment. So first of all, just to highlight the modulus. So it's as you would expect, we have an anisotropic material, and the initial elastic modulus is varying pretty much as you would anticipate for an anisotropic or transverse isotropic material. So it increases with certain angles, and it's lower at the 90 degrees away from that. Comparing with what Nick was showing with the DIW cubes, where we have programmed anisotropy, we can show that we can control the strain energy density through the printing direction too. So it's another degree of control we can have. Not only do we have a highly rate dependent system, like with what Nick was talking about, but that's controllable with the print angle. So if you want a really rate dependent material, obviously in this case we'll be using a sample which is printed at 0 degrees with respect to the loading axis. Flipping across to the DIW system, so this is using the DMA application inside with the electroforce. In this little demo here, I'm just comparing the behavior of our LCE to that of sorbothane. So the sorbothane chosen has a similar TG really to the LCE, and so it's kind of comparable. And the first thing you see is, first of all, another example of the rate dependency. So the LCE is showing a much larger variation in storage modulus as the frequency is increased. But what you're also seeing is how, especially compared to the sorbothane, but what you're also seeing is how that is again controllable with our print angle or print axis. Diving in a little bit more on looking at tan delta, you can see that for loading at 90 degrees, we're kind of seeing behavior that you would expect of a conventional or a typical elastomer almost. So as the frequency is increasing, the tan delta is decreasing, and we're having a more elastic material, which is becoming less dissipative. But if, on the other hand, we start looking at around between 0 and 45 degrees, we can see that we're still maintaining a very high tan delta, so very dissipative material. So not only do we have that rate dependency that we had from the storage modulus, but we're still having a very dissipative material too. So taking this ratio, so the tan delta over storage modulus, what we can see basically is how, if you compare with sorbothane, we have a lot of control over the material properties and the material behavior and mechanical response based on not only our chemistry, as Nick was saying, but also how we prepare that and how we print that with our DIW printer. So to summarize on that, we knew there's a lot to learn about LCEs. We knew that they are really complex in terms of how nonlinear they are, in terms of their anisotropy, and we needed to be able to characterize all that and understand all that to be able to look at real-world applications that we hope to pursue. And so really the electroforces allowed us to take, for instance, a single large sample from our 3D printing and then test that in a range of different ways with custom testing protocols to understand these highly non-conventional materials. So with
Great.
that,
Thank you,
I will pass
Nick
over to Chris.
So I'll switch gears a little bit and talk about a little bit more application-focused device kind of out of our LCEs. And I'll start with maybe this kind of heading saying that liquid crystal elastomers can change their properties over time. And we reported this in a study a few years back with Mohand being our first author on this. I see Mohand in the attendees list, so shout out to him. But what we noticed is that if we make these elastomer materials, they have a soft modulus. It's an elastomer, so think moduli around 1 or 2 megapascals. And so if we just put a weight on top of, this looks like a hollow cylinder, you could maybe think of it as a stent even. You put a weight on it, you can see it collapsed under a pretty small weight, about 100 grams. But with this chemistry that we reported in this paper, we noticed that over time, we could allow polymer crystallization. Right? Now, I know that's 2 different kind of crystals. You have liquid crystals and we have polymer chain crystals, but the chains would crystallize, and we would see a dramatic increase in mechanical properties. So on that bottom picture, you can see time's just much greater than 0. And with a certain chemistry, we just call it a C9 spacer chemistry, you can now see that the hollow cylinder or elastomer material could now withstand that 100-gram weight fairly easily. And so we went from a kind of a soft, flexible material to now more of a structural and rigid material. So we kind of thought on more recently with another one of my students, Ross Volpe, also recently graduated looking for a job. So anyone who wants to hire a talented PhD, hit up Ross. But we came up with this concept of how could we then take advantage of this changing of mechanical properties to treat some sort of disease. And so in this case, it was degenerative disc disease. A common method of treatment is to support your vertebrae and allow fusion to occur. So usually in between these 2 vertebrae in your spine, the disc or the soft squishy material degenerates and just for oversimplifying it, causes a lot of pain. And so the solution could be just fuse those 2, that joint together, prevent motion, prevent pain. And so I just have an illustration of the picture of the concept that you can see how a device is being inserted in between 2 of these vertebrae, and as it's kind of sitting there in the middle, it's supposed to kind of provide support to the bone. Now, there's some challenges if you talk to surgeons about this. They would prefer it to be minimally invasive, right? I think everyone can agree they don't want large incisions made on their body. It's better if you have a larger device. So that's right there kind of contradicts it. How do you get a large device in minimally invasively? That can be tricky. If you could make a device patient specific, everyone has different anatomy and I'll say geometry to their bones. How do you make it so these devices can match a patient perfectly? We want a high enough modulus that it could provide structural support. So 1 megapascal is probably not going to cut it. We need something much higher. And walking around, your back's a demanding environment. It needs to be resistant to fatigue and failure. And so we came up with this concept. I'll kind of walk you through it. Is if we 3D printed a cage, and so we used the direct ink writing approach that Nick talked about earlier. We could 3D print a cage. It kind of looks like a donut or kind of a hollow cylinder. As we do it, it'll start off soft and flexible. All right. And so that would give you the ability to kind of compress, or maybe even say squeeze in this large device through a small incision to promote the minimally invasive surgery. And then once inside the space, they call it the disc space, it could then expand and conform to the anatomy. So at the top right, you can see the cage, kind of an illustration of it getting kind of compressed or squeezed in through a small incision. And what we want is then after it's in, it would kind of elastomerically kind of recover, conform to the anatomy. So kind of fill in the spots because it's a soft material. It should provide pressure against the bone surfaces nice and evenly. And then over time, crystallize. And when we allow that polymer crystallinity to occur, we could provide support and now allow fusion to occur. On the right is just the illustrated concept and kind of shows the modulus will go from low, and I think in this case it started around 7 megapascals and would increase for just this one example up to 44, so a pretty large increase. So we had kind of two main questions that we wanted to answer is, how do the properties change over time? And when I say that, how quickly with our chemistries will the modulus increase, or you can say how fast is the rate of crystallization? And the second question is, could it withstand physiological loading? Like, is this just a pretty picture, a pretty concept, or could it actually survive the loads that would be experienced in your back? So to answer the first one, we typically go to DMA to do a lot of stuff. Now we had two different types of samples that we characterized. We had small strips, as you can see in the picture on the left, and this little sub-picture on the left, a small thin film strip, and we could characterize that in the Q800. I love the Q800. It's a workhorse of the machine. The Troy tells me I need an 850 now. I think Steve would like me saying that. But so you have this nice little strip. We could run that into the Q800, run a DMA sweep frequency or temperature sweep. But we also did 3D printing of cylinders, and we could use the electroforce to run DMA in compression on those cylinders as well. Now, the trick that we faced is we had multiple chemistries. In this case, I'm showing 3 chemistries to the right. You'll see a C6, a C9, and a C10. That just indicates different chemistries, really the number of carbons that we are tweaking in our spacers. But we want to measure them over a fairly long time period. And you can see from the graph, we're going to measure how the modulus is, or storage modulus, is changing over 100 or 200 hours. So to do that, I think most grad students, if you tell them, hey, you're going to have to run a test on the Q800, put a sample in there, and come back 200 hours later, I think everyone else in your lab will be pretty upset with you for hogging the machine for that long, especially if you're running multiple samples over and over again. One of the benefits we have with the electroforce is we have a pretty large heat chamber. And so as you can maybe see from how we plotted this graph out, is we were able to take a sample, get our measurements, let's say at a specific time point, 1 hour, switch out to the next sample, get that time point, switch out to the next sample, get that time point, and then store the samples in that oven over the course of this, let's say 200 hours of experimenting. So it allowed us to really have multiple samples running on one machine. I think the alternative would be, again, call up Steve Page, tell him you need a few more DMAs, Q800s, and try to run it simultaneously. That could work. But in this case, it was pretty nice because we took our 3D printed materials and we're able to characterize this kind of evolution of storage modulus for multiple samples kind of simultaneously. And so I thought that was pretty interesting. From the scientific standpoint, what we found is one of these spacers, the one that labeled C10, showed the fastest rate of, I'd say, increase in modulus. So within about the first hour, I'll say it increased from about 6 megapascals to 60 megapascals. And so we saw that just by tweaking or changing the chemistry, we could control that rate of crystallization and try to get it where it's approaching a pretty stiff modulus within a short time period. I've made the mistake in the past of trying to tell a surgeon that they'll need to wait before they could, before a device will work. They don't like to wait. Maybe an hour is still too long, but it at least seems somewhat feasible that they'll give time to implant this device, let it set, and then crystallize within a relatively short time period. It was nice by running these experiments out for 200 plus hours, because then when we wanted to do other sorts of characterization, just like your simple uniaxial testing intention, we knew how long we needed to, we could say, anneal our samples. And so we made sure that we aged them long enough to allow for complete polymer crystallization to occur before we then ran our tensils test. And this is just a nice little summary to kind of drive home the point that these materials have a pretty dynamic change in properties, going from soft and very elastomeric to, I'll just say, semi-crystalline, much more stiff, much more rigid. And so we saw a pretty dramatic change in properties that way. Our next question is, would this actually withstand cyclic loading? And really, how would the behavior, stand up to these repeated load-unload cycles? And so we tested two types of devices, and so I kind of zoomed in on them here in C and D. One was just a simple cylinder, very similar to what we ran for long-term DMA testing. And the other is our prototype device, this kind of prototype spinal cage. And for the cylinder, it was relatively easy. The grips or the platens they're parallel, so you can just simply insert that cylinder. These devices typically have a little bit of an angle to them, the device shown in D. And so we kind of just slightly modified how it was being compressed in that last picture to the right, marked in E. And you can kind of see we kind of could account for the angle of that device in there. Generally, what loads did we want to test under? We looked up from ortho load what the disc in your spine would typically achieve. What are the forces on it when under typical, let's say, walking. And so we found that the physiological loading at that area in your spine is between 140 and 280 newtons. So we set that as our kind of minimum and maximum force, and we tested at 1 hertz. We don't want to go too fast because, as Divesh pointed out earlier, these are viscoelastic materials, and testing at 10 or 20 hertz probably wouldn't be too representative. And so the nice thing with the electroforce is how you capture the data. Cyclic testing can be cumbersome, especially compared to testing, let's say like a traditional temperature sweep DMA or a uniaxial tensile test. Usually that's a very limited number of data, where I'll say maybe you only have anywhere between 100 and 1,000 data points. You typically don't have too much more than that. So very simple to maybe hold in Excel or a simple program like that. But when you're testing something out for 1 million cycles, you sometimes can get into like a data acquisition nightmare, if you will. And so you have a pretty robust way of how you want to capture your data. Of course, you could always just say continuously capture data at 10 hertz or 100 hertz. But when you're running 1 million cycles at 1 hertz, that is a long test, right? That test lasts longer than 24 hours for sure. And so you're going to capture so many data points, it could be very difficult to sift through. And so on the left, this is a nice option that we were able to select in terms of time data. So what you can do is you can capture an individual cycle. So in this case, you can see we captured cycle 1, 8, 128. You can see it increasing by some factor of 2 in there. But what you can do is then specify that you don't want to capture every single cycle for 1 million cycles, but you can capture cycles at a specific spacing or intervals. But when you do capture that, you collect a lot of data for each cycle. So it makes your management of data, I'd say, easy to do in that sense. And so we can then look at individual cycles spread out over the course of the entire cyclic test. And each then, you can look at each maybe hysteresis loop or load-unload loop with a lot of data points, but not have to go through and individually pull them out and just be kind of a death by data, if you will. So that's a very useful feature that we did. Now we saw for this tiny cylinder, as we ran this test, you might say, hey, what's going on here? you can see it ratcheted. They said this is ratcheting behavior. So as we kept loading and unloading, it was just kind of maybe stack on a little bit more unrecovered deformation. And so the cylinder slowly over time, you could say pancaked out. It compressed and got shorter and shorter. Generally, that would be bad in a surgery setting, that the two bones would get closer together as fusion was trying to occur. On the right, we showed a different way to capture data. They call this peak valley data capture. You can think of it more of capturing the minimum and the maximum values for each sine wave. And so in this case, it was pretty nice because you can capture that data very similar to, you don't have to capture it at every cycle. You don't need, we ran these to 1 million cycles. We don't need to capture 1 million data points. But we could kind of space that out and say, hey, capture where's the minimum displacement and maximum displacement at periodic time points throughout the test. And so this was pretty nice because for the cylinder, if we look at the bottom set of data, it kind of captured what was going on the left. You can see how the device started at a certain height and kind of compressed over the course of 1 million cycles. But for our prototype cage, and naturally it has a much larger surface area, so the stresses on that cage will be lower, you can see that ratcheting behavior was largely minimized or mitigated. So we could say that it is, not a surprise, but the device is kind of dependent on your surface area. But if we do allow this prototype device to crystallize, and we have this, I'd say the required amount of surface area or an appropriate amount of surface area, then we wouldn't see ratcheting behavior that definitely not as detrimental as shown in the cylinder. So the benefits kind of from this study is, we used the DMA function of the electropores to measure the rate of crystallinity, or how fast it was crystallizing over that. And we could track the storage modulus for over 100 hours, and we didn't need to maybe have the machine running continuously for all 3 or more. It was definitely more than 3 samples, but multiple samples for very long stretches of time. We could run them simultaneously, which was nice. And our cyclic testing, could actually match physiological loading. Now, I get there's some joints that will experience more than the capacity for the electropores, but for this being, I'd say a common medical device, spinal devices are very common. We could match those ranges of, I'd say, pretty demanding loading, and so I think it's all the way up to about 500 newtons of which force it could apply. And then I would argue that for the cyclic testing, I think this is one area where the electroforce really shines, is just the ability to capture data for you to analyze it and use it in a useful manner quickly is a strong point for the machine. So I'll try to wrap up our presentation. I know you guys have been with us here for about an hour. Thank you for your time, for sure. Hopefully you've learned a little bit about LCEs and maybe at least spark some interest that you may have heard of them as actuators, but I would say they're definitely more than actuators for soft robotics. I think from just a unique mechanically active material, they can experience soft elasticity, they can be highly anisotropic, and then when you combine that with 3D printing, you can make some pretty unique materials and samples. But of course, with unique materials and samples that you can print comes the need to characterize. So after you make it, you always have to characterize. That's how we publish, right? So I hope that you enjoyed just different techniques we've used to either quantify things like energy dissipation or rate dependence in elastomers, looking at the dampening as a function of how we printed it, or you could say print orientation or pathways, and even just looking at things like long-term DMA testing, for not just maybe the typical hour for a temperature ramp, but a 100-hour test, and also using it to do cyclic testing with, I'd say, large physiologically relevant forces. And so I hope we've acknowledged enough people in here. Now, I know we've probably forgotten some people, and it's just because I'm an absent-minded professor, so if I forgot to acknowledge you, my apologies. But we've had some good funding from the NSF, the NIH, Colorado, the Army Research Office, Sandia, and the Lindman Trust Fellowship. We had a great team. I kind of mentioned that we had a couple collaborators even on here at Mohand. Thank you very much for being my student, and I think being more successful than me now. Some of our collaborators at Impressio and University of Wyoming, Johns Hopkins, and Kevin G. So yeah, we'd like to thank everybody. So I think now, I'll do one more question. Yeah, we'd like to open this up for questions, and be happy to answer anything that you might want to throw our way. Thank you again for listening to us.
All right, guys. Thank you very much. Yeah, that was excellent. Yeah, we have a number of questions, so if you're good, we will just roll right into that. So I'll start with a question, pretty quick one, I think. What is the cross-linking agent for LCE?
Cross-link these materials. When we do the 3D printing, we always have, I'd say, unreacted acrylate groups. And generally for both these printing methods, we're using UV light. And I won't say UV and photo cross-linking always involves acrylates, but it more often than not does. I might make that argument. And so in these cases, our resins end up getting cross-linked, both the DLP resins and the direct ink writing resins get cross-linked because we have these excess acrylate groups. We shine that UV light, and that forms that cross-linked network into our materials.
Okay, perfect. Another question, since these are UV cured, I'm assuming the final products are not biodegradable. Is there any way you can make them biodegradable?
That's a good question. It's definitely an area that we haven't explored, but I would say maybe in general, I'll say polyethylene glycol cross-linked acrylate networks. I'd say we're pretty famous maybe in the early 2000s for being biodegradable and for as like a therapeutic. And our chemistry is not too far off from that. Right? A lot of those biodegradable acrylate networks were made through photo curing, and what we haven't done to date, this kind of just isn't maybe our wheelhouse or our expertise, is putting in some biodegradable spacers within our network. But this chemistry has been relatively flexible for us to do that. So really, if you can find a biodegradable linkage with either acrylate functionality or thiol functionality, those are just two examples. You could then substitute that in or add that into our starting chemicals relatively easily. I think that's one thing that I keep mentioning Mohan. Mohan and I really tried to develop with these systems is the tailorability and the ease of tailorability of these systems. So I don't see anything stopping really anyone from finding a nice degradable linkage just with either, like again, thiol or acrylate functionality, and then kind of incorporating that into our initial chemistry and making it biodegradable.
Okay. Another one here. Let's see. Regarding slide 32, you talk about crystallization. How do you know this crystallization has proceeded? Does the crystallization just proceed after the elastomer has been polymerized over time, without any manipulation of conditions?
Naturally, I left just maybe a few details out. I tried to focus on the I left just maybe a few details out. I tried to focus on the electrophores a little bit more. So what we did to kind of characterize that crystallization a little bit further, or even just understanding that, hey, there's a polymer crystallization going on. Maybe the first maybe thing that came to mind is we polymerized the samples, and you're like, all right, these felt like traditional elastomers. And then we came in the next day or a couple of days later, and you're like, holy cow, these things are all of a sudden really stiff. What's going on? So we did run some, I'd say, temperature ramps on the Q800. Gotta love the Q800. And what we found is, as we'd run those temperature ramps for samples that were sitting on the counter for several days, we noticed there was a little bit of a how do you say, the storage modulus was higher, and then there's a very dramatic drop in it that we're like, hey, that kind of looks like some crystallinity melted. Then we went to the DSE and ran some samples and actually measured out. There's a very large enthalpy change there that looks a lot like crystallization. And Nick has informed me that my dog is snoring next to me, so I apologize if you guys hear any rhythmic snoring in the background. This is what we get for working from home now. But no, we ran both DMA and DSC to verify there was a polymer chain crystallization going on. In terms of working with conditions, what conditions are needed, generally we needed to be above the glass transition. So I would say it's relatively passive because for these materials, ambient temperature is above glass transition. As long as you didn't freeze them, it would occur. So generally the sweet spot for allowing it to occur was above TG, which is about 0 Celsius, to about their crystallinity melting point, which was about 55 Celsius. So that was it's relatively, you don't have to do much to maintain the temperature in that range.
Okay.
I woke my dog
Another one
to stop her.
um, how do you actually relate stress strain test to the drop test? The strain rate in the drop test must be at least an order of magnitude greater than what you can achieve on the electroforce instrument.
Yeah, so that's a great question. Because you think impacts happen really quickly, and so um, uh, I'll maybe mention a couple of things. The electroforce is real nice because you can obviously go as slow as you want, right? You can make these tests. I know our slowest rate was 0.2% per second. We could have made that much slower. Yeah, my students sometimes will yell at me if I ask for that, but we could go slower. And we then got strain rates on the high end around, I'll just say it was around 220% per second, if I remember that right. If I look for what the actual speed is, if you looked at the displacement rate of the crosshead for when you're doing that, it's usually around a half a meter per second, right? And so, maybe give or take a little bit there, but the electroforce moves at about as quick as it can move, is about a half a meter per second, which is still really fast. If you looked at the drop testing that we do, most of those are usually between 3 and 6 meters per second. So you are right that it's about an order of magnitude off. So you could say a half meter to 5 meters per second. Yeah, about an order of magnitude off. The nice thing that we have noticed, though, with these materials is that rate dependence is relatively, I'll say, predictable. And so if you were to plot, let's say, the stresses as a function of your strain rate on the log scale, it's power fitted really nice. And so it allows us to kind of extrapolate that out without having to run the drop test fairly quickly, really quickly, actually. Running drop test, I'm not saying it's the most intensive test to run, but the electroforce is definitely much faster. So I would say it kind of gets all the way up to knocking on the door. Again, you get about a half meter per second. And if you then run a suite of tests at slow rates all the way up to about that half meter per second, it kind of falls in line very nicely with the rate dependence, and you can pull that out. Now, naturally, what we'll do is we still will run the drop test and try to fill in those gaps in data, but it's just a lot faster to kind of maybe characterize that space, and it gets you really close to the speed, and then you can just extrapolate out, which is nice.
All right, great, yeah. One last question. We're almost at the top of the hour, so I'll just finish with this one. Have you tried augmenting DIW nozzles with electrodes and altered designs to achieve cross-flow loads LC alignment directly in the print bed rather than just through the changing the print direction?
I'll let Nick probably answer that, but I'll just say, hey, make sure we're writing that down. That sounds like a great idea. Yeah, Nick is definitely our expert on the DIW printing. Dee maybe is a very close second, but Nick, I'll let you see if you want to respond to different things you've tried with nozzles and print parameters.
I would actually say Divesh trumps me on the DIW at the moment, since I've heavily worked on DLP. He's definitely our resident scripter and stuff, so I'm actually going to pass it off to Divesh.
That's a good question, though.
All right, then I'll take it. So I guess with the regular low molecular mass liquid crystals, alignment with an electric field is very possible. If you're going to try and do that with DIW, I think it'd be difficult. First of all, to set up your experiment and to achieve a large enough electric field to do that with the viscous ink. We're mixing a few things in ours and trying to print with a relatively large nozzle size. So in the other examples of 3D printing of LCEs, you're talking about a 100 to 200 micron nozzle. We're starting at the minimum of about 500 micron nozzle. So to get a field strength large enough to cause alignment would be pretty difficult there, I think. It would be very interesting, and it would be great if you could do it. I think for us, it's something which is a bit beyond what
I got one that came in just now. That's a pretty good one, I think. We'll finish on this one. Did you choose the LC materials based on how close the pneumatic temperature range and the glass transition temperature of the elastomer?
Make sure can you just say that one more time? I want to make sure I get all the details.
Did you choose the LC materials based on how close the pneumatic temperature range and the glass transition temperature of the elastomer?
Yeah, that's a good question. And I maybe say I tend to be a guy that likes to choose systems, right, with a lot of tailorability. So what I mean by that is, I think if you look at some of our previously published papers, you'll see we spent maybe considerable effort showing, hey, this is how you get that pneumatic to isotropic temperature to be as high as say 130 Celsius and as low as body temperature. Or as we change the cross-linking conditions, this is how our glass transition can be as low as negative 10 C up to as high as 40 C. And I think there are some papers out there even showing that the glass transition can get down into let's say that negative 40 or 50 range even. So I kind of maybe say I like to characterize that system to show we have tailorability. I'm a very applications-oriented approach in the way that you never know exactly what requirements a customer might have or a specific problem might have for requirements. Maybe it wants your TNI to be right at body temperature to take advantage of maybe that transition and be in that sweet spot. Maybe not. Maybe you want that isotropic transition temperature to just be well above where you're operating. So maybe it's a little bit of a dodge of a question, but I think more we try to show is that the system as a whole for these liquid crystals are highly tailorable, and then that just gives you a lot of not always freedom, but gives you a lot of options and potential for designing around a specific application. Yeah, I'll say it that way.
Yeah, that's good. That makes sense. Okay, well, thank you guys. Great job on the talk and fielding all those questions. Thank you, everybody, for your attendance, and just wish you all a good day. Bye, everybody.